On a recent job I had to find a solution for finding a path through a way of objects. And I want to talk about this naive approach to pathfinding here a bit. So this is the core of our problem. We want to get from a start point to an end point, like here. However, we have the problem that there are obstacles in our way, like so, drawn these blue circles here. And there are obstacles. While moving from the start to the end point, we want to avoid them. A bit like so. So we have to find a path around them. And my approach, which is quite a brute force approach, but which works most of the time, is the first step is we scatter points around those objects. We fill the space around those objects with points. And the more points we have, the better, and the more evenly they're spaced apart, the better. So the first step after we scattered those points is from our initial active starting point, we find a bunch of close points, like in this radius here. One of those points is the next point in our path, so we have to now decide which one to choose. And the way we do that is, first we draw a vector from our currently active point to the end point. And what we'd like to do is to choose a point which lies on this given vector as closely as possible. So in order to find out which point does that, let's zoom in a bit here. We draw vectors from our currently active point towards all the points we found. And in the next step, we compare their angle to the direct vector, to the endpoint. And as we can see here, for example, for this vector, the angle is quite big, and for this vector it's even bigger, and drawn from this side, the angle to that vector is almost as big as this here. And what we find out is that this point yields the closest angle between the direct vector and the vectors of all that points we found. So this is the next point in our path. And from this point on, we just repeat the whole algorithm. So again, from this point, we're looking for close points, draw a vector from this point towards the end, and compare all the other vectors pointing to the close points to that direct vector. Again, this is a very naive, very brute force approach, and it really depends on how much points you scatter in the beginning. The denser this point cloud, the better the path this algorithm finds, because it has much more options to choose from. So let's implement this. Inside of Houdini, let's first drop down a geonode, dive in there, delete that, and the first thing we're going to do is create those obstacles. And in our case, I'm just going to use a sphere, make sure it's set to polygon, and increase its frequency, like so. Duplicate that, and create a basic volume with the help of an ISO offset, just really quickly, really coarse volume. And let's scatter points into that volume. Let's dial down the number of points, and let's switch off point relaxation at this state. So we get something like this. Next thing I'd like to do is give the points an attribute. You could do that with an attribute create. In our case, I'm just going to use a point wrangle. Wire that up. And drop down this little expression, create a float called pscale, and that is going to be fitted between 0 and 1, and the output value should be in 0.05, and let's say 0.3, and the value that we're going to fit will be this. Random, and as a seed, we'll get the point number, and we'll add to it an integer, which we'd like to adjust, and let's create a channel, an integer channel, that's CHI, and let's call this one seed. Hit this button here to create the channel slider that we just defined here. There it is, expression works. Let's just make sure and check in the geo spreadsheet. Yeah, my p-scale is there, perfect. And now I'd like to relax this thing with a point relax. And the reason I'd like to relax it now is now I've created the p-scale attribute, and point relax can take that into account when I make sure that point radius attribute is set to p-scale, and I make sure that relax in 3D space is checked and increase the maximum iterations to say 200. Highlight that, and we got our points relaxed now. Now these are my template points. Let's feed them into a copy SOP. Wire them up in here, wire the sphere up in here, and highlight the copy SOP. And I have now non-intersecting, almost non-intersecting spheres scattered in here. So let's dial down the sphere radius a bit to make sure that there's some space between them so they absolutely do not intersect. That looks good. And now let's turn this into a VDB. With the trusty old VDB from Polygons, let's just dial down the voxel size a bit. And also we'd like to create another VDB that contains the area, the space, where the points that we need to find our path through will get scattered into. So let's just drop down another sphere. Goes that. And dial up its scale a bit. Something like this, yeah. Maybe a bit too big. More like so. Let's turn it into a polygon, increase its frequency, and just copy this VDB from Polygons here. Wire this up in here. And let's go back to this one, because I've noticed that when turning this into a VDB, we still get some intersections here. So let's dial down our sphere radius a bit further. We could also increase the VDB resolution, but that would slow down our setup. So let's just decrease our sphere size and make sure they absolutely do not intersect. Okay. Now what I'd like to do is carve out those spheres out of that general surrounding volume here. So let's do that with a VDB combine. Wire up both VDBs in here and set it to SDF intersection. No, we want to set it to SDF difference, and we would like to put this over here, make it like that, and we would like to subtract this from this, like so. Okay, let's drop down a volume slice here to check. Yes, and we see we got a volume with those small spheres carved out. Great. Delete that again. And let's turn that volume, which is still is a VDB, so it's a surface, let's turn that into a fog volume with a convert VDB node. Wire it up and set it up so it converts to a VDB. It can stay a VDB, but it should be changed from SDF to fog, like that. Okay, the whole operation we did there was just to generate, on the one hand, the obstacles that we would like to avoid when doing our pathfinding, and on the other hand, the volume that contains the space where those points where our path can run through will get scattered into. So let's scatter those points in there with the help of a scatter sub again. Highlight this, and let's dial down the relax iterations to something like 4. In a perfect world, I would keep those relax iterations rather high and even increase them past 10, so the points that will be created get really uniformly scattered in there. But as I'm going to increase the point density, this will take too much time for my taste, so I'll just dial back the relax iterations and increase the point count to, say, something like 100,000. Now, there are two things that we still need, which is a start and an ending point. So let's create those with the help of an add. And let's just call this add start, copy it, call this one add end. So let's add a point here with the add start node and enable display points here, and move that point that we just created up a bit so it sits on the outer edge of our scattered points. Do the same thing with the endpoint. Let's just move that down for our case, a bit like so. So now, in order for my algorithm to work, I need two groups. And let's just shortly go back to the Illustrator file. On the one hand, I need a group which tells me which is the active point, or if a point is active. So if a point is this point where I'm searching for the scattered points and where I'm comparing the angles. On the other hand, I need a group which tells me which points are the path that I already traveled, so I keep them in mind for later for connecting them. So let's just quickly create those two groups. Let's create a group called active, and it should be a point group, and we're gonna add this starting point here. Let's duplicate that For all my scattered points, I want them to be not in that group, so let's put an exclamation mark in front of the star symbol here, which tells Houdini to put nothing into this group. Check again with the geo spreadsheet. Okay, none of the points is in the group active, that's perfect. And let's check here. And my single point is in the group active. Perfect. What I want to do now is merge those two geometry streams here with a merge node. So I have one point cloud. And I want to wire in the starting point first and the inactive points second. And what that does is it makes sure that my starting point will always have the point index of 0, which is just a help for me. Now we're all set up to do some vex wrangling. And again, let me just illustrate what we did here. First, we scattered points in the volume that we created. Then we assigned them a p-scale value, relaxed them a bit according to the p-scale value we just assigned, and then copied spheres onto them. Turned those spheres into a VDB, created a sphere surrounding all those other spheres and turned that into a VDB as well. Then subtracted the copied spheres from the outer sphere, turned that into a standard volume, scattered points into that volume, grouped those points to be non-active and merged them with our starting point, which is active. Now let's create the algorithm. Let's drop down a point wrangle and write some of my beloved vex. And what I'd like to input here is on the one hand the point group containing the starting point and the inactive points that we can use to find our path. And on the other input I'm going to wire in the endpoint. Let's highlight this and select it. And when I take a look at the diagram here, the first thing I'd like to create is this vector here, pointing from our currently active point towards the endpoint. So let's create this vector by writing down a vector. Let's call this target TGT equals our current point's position minus the position of the point coming in through this second slot here. And we get that by dropping down a point. Slot numbering starts from 0, so this is the first slot, 0 first. So let's drop down a 1 there. The attribute we'd like to get is the P, and the point number will be always 0 because there's always one point coming in there, so it's always going to be the 0. Now, I want to execute the algorithm only if a point is in the group active. So let's check that first by dropping down an if statement, and in here dropping down a vex function called inPointGroup. And again, if you don't know which parameters this function takes, just make sure your pointer is in that parameter name and hit F1 and the contextual help will open. So this is going to take the input slot, so 0, the group name and the point number. Okay, so 0, group name is active, and the point number is our current point number. So if that is true, then do all of that, what's going in those curly brackets. And if you remember our diagram, the first thing we'd like to do is find points in a given radius around our currently active point. So let's do that. We do that by using a function called pgfind, which is a faster version of pcfind, which a highly talented guy called Max pointed out to me. I'm not sure if he has a portfolio, if so I'm going to link it, but this is a hugely talented guy, so make sure to keep an eye on him. Okay, the function we're going to use is pgfind, and we're going to search in the 0th input slot, and again let's just press F1 to open up the help file. So what we're going to use is this expression here. We will look into the incoming points from slot 0, and we will search only points that are inactive. So the way I'm going to put that down is I'm going to specify the group name, but I can use the same syntax as, for example, in our grouping node and just put an exclamation mark in front of it. So that's going to look only in the group non-active. I'm going to search for points around our current position. And I'm going to search for points in the vicinity of the radius. So let's call that search rad for search radius. And we'll find a number of maximum points. So let's specify the maximum points we're allowed to find. call them max PTS, and the div size in most cases can be set to the same as the search radius. So let's drop down the search rad again, and up here specify those two variables that we just used, search rad and max PT. So like so. And this will return an integer array, so we'll have to create a variable for that as well. Like so. Now, this expression finds all the close points in the vicinity of that point within the radius that we specified, and creates an array of them, so creates a list out of those points that it found. And what I want to do now is go through that list, and for each point compare the angle of that point towards the direction vector that we created. Let's first go through those points. I'm going to do that with a for each loop. And I'm going to create another variable called, let's call that CPT for close point. And I'm going to go through all those points queued up in close PTS. Back in our diagram, I see the next thing that I need to do is create this vector here from our currently active point towards the found points. And as I'm stepping through this list of found points, let's do that for this one point that we're currently working on, and create a vector called current point target. And our current point target is our currently active's point position minus the position of the current point that we're working on. We're just going to use this expression here. Let's just copy it, paste it here, and change it to work on our 0 input slot and on the point ID that is saved within current point here. So what I just did is just create one of those purple vectors here. The next thing I have to do is compare this vector. This is the purple one that we just created with this orange vector here. And the orange vector is the one we created here, the target vector. So we have to find out the angle between the current point target vector and the target vector. And we're going to do that by using a bit of trigonometry here. And we'll create a variable called angle. And it's going to be the arc cosine of the dot product of the normalization of two vectors. One is my target vector, the other one my current point target vector. So this expression will give me the angle between, in our case, one of those purple and the orange vector. But remember, we're still working on that array, we're still working on that list of close points, so within that list we need to find the point which will yield the smallest angle when doing that whole calculation. And the way I'm going to do that is by creating another variable up here, and let's call it old angle, or short O angle. And let's set it to something really high, like 1000. And down here in our for each loop, where we're going through this array of points, let's drop down an if statement. And we want to check if our current angle is smaller than our old angle. And if so, let's set our old angle to be our current angle. So this way we make sure, while working through a list of points, that as soon as we find a point which will yield a smaller angle than the previously smallest angle, it will get written into the old angle here. However, in parallel, we also have to write down the corresponding current point ID. And we're going to use the same technique here. Just create another variable up here called, let's call it next PT, and set it to -1 initially. So this is not a valid point ID, so it won't yield a valid point. And if we found a smaller angle here, set the next point to be our current point. So we will save out the angle and the according point ID in here. Okay, now we found our point with the smallest angle, and we want to set that to be our next active point. I'm going to do that by using the set point group. Working on a 0 input slot, we want to set the point to active, and we also want to make sure that the point we've been working from, so the active point that we've been searching from, will be set to inactive by just copying this expression, pasting it down here, setting this to 0, and of course we need to add point IDs in here. So our next PT will be set to active. That's the point yielding the smallest angle that we found, and our current point will be set to 0. And that should be it. Let's save and check if that works by creating a solver, wiring in the merge on the one port and the endpoint on the other, and just copying our vex code into the solver, wire up the previous frame in that slot and our endpoint in the second slot, go up one level, highlight it. Well, let's hit play. And nothing happens. All I'm doing at the moment is changing point groups. So when I want to display something happening there, I'm going to need to add a delete node. And I'm going to delete points that are not in the group active. So I say delete non-selected, and I have only the group active selected now. What I have now is a point wandering towards the endpoint. However, it's not leaving a trail behind, and that is because we have not created a separate group for the trail or for the path that we're traversing. So let's do that, and I'm just gonna add our point wrangle. We only need it in the solver. Let's create another group called path. Again, it should be a point group, and in the beginning there should be nothing in it. Let's just highlight it and check. Okay. And within our solver, we want to make sure down here that on the one hand, we set our previously active point to be now contained within the path by using a similar expression to this. Just change the group to path, and our previously active point that we've been working on in this vex expression should be set to be in that path group now. On the other hand, up here, we want to make sure that we only find points that are not in the active group and not in the path group. So let's expand this expression here and add a Boolean and we want to exclude points which are in the path group. Again, what I did here is just telling the pgfind to find points which are not in the active group and not in the path group. Okay, the delete node needs to be changed so it deletes everything but the path group, like so. And now, you see, we're traversing those points till we find the end node. Let's just wire this into a merge node, and also wire in the obstacles that we created in here into our merge node. So we can see that our path is not intersecting any of those spheres here. As you can see, it's moving close to the surface here, but it's still moving around those spheres. So let's expand that a bit and add more than one starting point by abusing this volume that we created here and just copying the scatter. Dial down its point count to say 20, and maybe give it another seed so the points have another position. And wire this into our starting point group in here. Reset the whole thing, highlight the delete node, hit play. And we see all those points will now try and find a way to the endpoint that we defined. Again, highlight our merge node, and we see none of those paths are actually intersecting the spheres that we copied. So this is the basic Pathfinder setup. Again, very brute force algorithm, but one that will yield results that do not intersect with the geometry that you give it. Again, let's dive into the solver and into the point wrangle, and let's go over a code that we created one more time. Up here I defined my variables, I defined the search radius, I defined the maximum points that we will find when searching for points around our active point. I initialized my old angle with just an angle that's absurdly high, so it will always be overwritten. I initialized my next point value with a negative point index, so a point index that doesn't exist. I specified my target vector as being the vector pointing from my current point towards the end point. And then for every point that I find that is active, currently active, so this is the point in our path that is in the front. For this point, I'm looking for close points surrounding it within the vicinity of search radius, search rad, and I will only look for max PT points. So in our case, I'm only looking for 32 points, and I'm looking for points that are not active and that are not in the path group. All these points get written into this array, and the for each sub will work itself through this array. And for each list entry in the array, will on the one hand calculate a vector from that point pointing towards the endpoint. Then we'll calculate the angle between this vector here and our target vector. And then we'll find the smallest angle there is and set the O angle and the next PT variables to contain on the one hand the smallest angle it finds, on the other hand the point ID of that point yielding that smallest angle. And this point yielding the smallest angle is going to be our new active point, so we will set this point to be active. We will set the old point that we've been working from to be inactive now, and we will set the old point to be in the path group now. So, this is the basic algorithm. Again, a rather brute force approach, but one that works for most of the time, depending on the point density you set. In general, a higher point density will yield better results for the path. Also, what you can try is not scattering the points that the path will search through, but creating them, for example, with a volume to point sub, thus yielding a very regular point distribution, and maybe yielding more interesting patterns. So I hope you have fun with it. Again, if you produce any artwork using this, we'll be really glad if you send us a link or tag us or send us a message. We are always excited to see what you guys come up with. So it's cheers and goodbye.